So we're going to talk about exponential growth and decay. We've been talking about that the past couple of days. But today we're going to put it down on paper, all the rules. That way we have somewhere we can go back and refer to for these rules. You ready? All right. So the parent function, and I introduced this a little bit yesterday. The parent function for exponential functions is y equals a times b to the x power. And then what we're going to do is we're going to talk about what that a and b each mean. So the a value we saw on Monday when we were finding the number of squares and the area of the squares is the initial amount. Excuse me. So that's how much you start with in the problem. Yesterday we saw that it was also the y-intercept. All right. So yesterday we saw both when a was bigger than 0 and when a is smaller than 0. When a is bigger than 0, our y-intercept is positive. When a is smaller than 0, our y-intercept is negative. We are going to more often see when that y-intercept is positive. Sometimes we'll see it negative, but most of the time it's going to be positive, especially this week. All right, and yesterday we also talked about a cannot be 0. Notice here, a is either bigger than 0 or a is smaller than 0. So a cannot be 0. What happened when a was 0 yesterday? It was a straight line. We had a straight line. All right, so the b value tells us about the growth or decay rate. So it tells us how fast something is growing or decaying. Usually we'll hear things in a word problem like half as big, twice as big, 22%, things like that. And we're going to talk more about those tomorrow and how to write those. So yesterday we decided when b was a fraction between 0 and 1, we had decay. And when b is a number bigger than 1, we have growth. The notes are on your desk. The notes are on your desk. All right. I have one more vocabulary word for us that we're going to use here in a second. Asymptote. We talked about that a little bit yesterday. what an asymptote is, when we graph it, it's a dotted line. And we know that the exponential function never crosses or touches it. So I'm just going to kind of abbreviate here. We're going to say a dotted line. Function does not cross it. And we're going to do an example of that in just a second. You okay, hon? Okay. All right, so I've got a space there for growth and a space for decay. So we're going to do one of each. I'm going to scoot this up just a little bit. There we go. So let's do an example of growth first. So growth, yesterday we talked about, if we're reading the graph from left to right, is the graph increasing to the right or decreasing? Increasing. We said it was going to increase to the right, so. Okay. We also said that this point here where it crosses the y-axis is whatever the a value is. And I'm going to add in that asymptote. I know, right? It's okay, it's a function. So notice here that my exponential function is decreasing to the left and it's getting closer and closer and closer to that dotted line, right? That's the asymptote. It'll never cross it, it'll never go to the other side, and it will never touch it. And I'm going to write the equation of that asymptote just because it's good to know. This one is on the x-axis, so my asymptote is y equals 0. Asymptote. There you go. Uh-huh. All right. So let's go ahead and do one for decay. So decay means when I read from left to right, the right side is going to be decreasing, right? So this one's going to start tall and then get shorter. Again, it's going to cross the y-axis at the point 0, A. And it's going to get closer and closer and closer to that asymptote. It never touches it. So, so it's going to look like it's straight, but it's actually decreasing just a tiny, tiny, tiny bit. So it's decreasing so slowly that we can't see it on the graph. Does that make sense?
But it does touch. If it's
No.
going forever, then it does touch.
No, that's the idea. It doesn't. It can't. Because it'll never be 0.
But if it goes down a little bit, eventually in time, it'll get there.
All right. And then that y, the asymptote, the equation for our asymptote here is y equals 0. All right. What we're going to do next is I want to talk about the domain and the range. And we're going to do a couple of examples for each. So let's talk about growth first. We talked about domain and range yesterday. So here, we're pointing to the left. It's going at forever, right? So do we have a smallest value? No. So what would I call that? Sure, we could call that negative infinity. And it's positive infinity rules because it's going up and to the right, yes? And as long as it's going up, it's going right. So to positive infinity. Perfect. All right. My range. So let's look at those y values. So like we said, if we look down, this is getting closer and closer and closer to 0, but will it ever be 0? No. So it's all of the y values bigger than 0, right? But not including 0. So I can say y is greater than 0.
Can I say 0 is less than y?
Sure, you could say 0 is less than y. No, it doesn't. All right. Now I want to do an example. So here, the first thing I want to see, like I said, our a values are going to be positive for the most part this week. So I'm going to go ahead and make this positive. And if this is growth, what do I know about that b value?
It's gonna be
Well, look at our notes. If it's growth, my b value is greater than 1, right? So let's see here. I'm going to do f of x is equal to, I need a positive a value. Give me a positive a value. 2 times, and then I need a number bigger than 1.
5.
I was gonna say
5 to the x power. That's an example. I want you guys to write another example for me. Come up with one more example for growth. One more example for growth. No, you can change your a value. Anything you want. So give me one more example. Oh, those are good examples.
Oh no, you gotta be kidding.
I never kid about math. Beautiful. That's a good example. Oh, look at that one. That one works.
Doesn't matter. Oh crap. Doesn't matter how you write it at all.
What do you mean?
I mean like the numbers that we choose.
No, any numbers you want.
Charles, can you maybe go up? I didn't get a good
It'll be on Google Classroom later. All right. So now let's talk about decay. Let's talk about decay. So my domain, again, is going up and to the left. So as long as it's going up, it's going left. So do I have a smallest x value? No. And then it's kind of flattening out and going down a little bit to the right. So do I have a biggest x value? No. So do we have the same domain?
Yes.
It's the same domain, right? Is there another way to say negative infinity to positive infinity for the domain?
All the numbers.
All real numbers.
All the numbers. What if they're not real?
They're all real.
Our imagination.
No. There are imaginary numbers, but you won't see them. Yes.
Like what? Yeah, actually.
The square root of -2.
What's that?
Imaginary.
Whoa.
All right. What about the range? Did my range change? No, it's the same again. So it's all of the positive y values again, right? I want to say
But like the thing he's gonna
y is great. No. It's still all of the positive ones, so it's still greater than 0. You got it. So even though growth and decay, the graphs look different, the domain and the range are both exactly the same, right?
Can I put for an example f of x?
Sure, let's do f of x.
7 times 15 or 15 squared.
Well, wait, not 15, because look, if it's decay,
Oh, and it has to be a negative?
no, look, if it's decay, it has to be a number between 0 and 1. So instead of 15, we could use
0.37.
0.37 or 0.15 or 0.5, right? So let's do, you said 0.37 to the x power. Beautiful. All right, I want you guys to come up with one more example for me. One more example.
Can I put the one that I said?
Yes. Good. Seeing some nice examples.
Okay, so come back after school.
I don't like coming to school, but I don't like summer because I actually kind of like learning. It's weird.
All right. So what we're going to do now, you guys, is we're going to take a look at some equations and some word problems, and we're going to decide if they are growth or decay. You ready? So look, all of your examples are on the back today. So example number 1 says, do the following exponential functions represent growth or decay, and how do we know? How do we know? So, hold on. We were just talking about growth and decay. What was the one number we had to pay attention to decide if it's growth or decay? The A or the B?
The A.
B.
I mean
The B value, right? So, let's take a look at A. A says f of x is equal to 2 times 3 to the x. So, my B value is 3. So, we have to ask ourselves, is 3 bigger than 1 or a fraction between 0 and 1? Bigger. So, if it's bigger than 1, it's growth or decay? Growth. There we go. B is bigger than 1. All right. What about B? 1/2 times 6 to the x power. Growth, because B is bigger than 1. C says g of x is equal to 2 times 1/2 to the x. Decay, because b is what? 1/2, which is less than 1, bigger than 0, right? So I've got decay. All right. Last equation. K of x is equal to 1/4 times 1/2 to the x power. Decay again, because b is 1/2.
It could only be decay if it's 1/2.
Not if it's 1/2, if it's a number between 0 and 1. All right. I'm almost done, Jules. Almost done. You ready? All right. Last example. We're going to look at some word problems. And we're going to look at some word problems and decide if these exponential functions represent growth and decay. And we're going to tell how we know. Okay? So what we have to do is we have to look for some clue words and use some logic. You ready? So A says, you start a bank account with $500 and an interest rate of 6% compounded yearly. So what this means is you go to the bank and you put $500 in a bank account, right? What does this interest rate of 6% mean? You get 6% each year, right? So are you making money?
You get 6%
Of what's in the bank, of all the money. So every year they reevaluate how much money they're going to give you.
6%
Of 500 the first year, and then the next year you get 6% of the 500 plus what you got last year. And the year after that you get the 6% of the 500 from the first year plus what you had last year plus this year. Does that make sense? Kind of neat, right? So every year they're going to pay you more. So are we growing our money or decaying our money? Grow. All right. B. B says from 2000 to 2010, a city had a 2.5 annual decrease in population. If the city had 2,950,000 people in 2000, determine the city's population in 2008. So what's happening here? Decreasing? How do we know? What word tells me that? Decrease. So is that growth or decay? Decay. So people are moving away from a city. We have exponential decay. C. D says a newly hatched channel catfish typically weighs about 0.06 grams. During the first 6 weeks of life, its weight increases by about 10% each day. So it's increasing, so that's going to be growth. Perfect. All right, last word problem. You ready? D says your dream computer costs $3,200. You find that depreciation is 8% per year. Decay, because depreciate means to decay. Appreciate means to grow. Depreciate means to decay. You got it.